Go. Hello and welcome back to Calculus 1, section 4.7, there we go, on L'Hopital's rule, which is actually Bernoulli's rule. If you want the full story, just watch one of my previous lectures. I have the full story in pretty much every single one. So, what is this L'Hopital's rule? It's a way to take derivative for sine and cosine. At one point, it was stated that the limit of sine x divided by x as x goes to 0 is equal to 1. And it was simply said, remember this, and eventually we will talk about it. Right? Well, hello, eventually, right? That's tonight. So what is the way to solve this particular limit? Well, we have what we call indeterminate form in this case. The easiest way to solve limits when possible is to plug in the value you're approaching, and if that works out to be a straightforward calculation, you're done. If you end up with 0 in denominator or any kind of other extraneous situations, then you have to use something else. Well, for L'Hopital's rule, when you plug this 0 in, sine of 0 is 0, and you plug in 0 for x, you get 0, you get indeterminate form 0 divided by 0. And we'll see that we have two indeterminate form. There's also infinity divided by infinity. This is insanely important for your Calculus 2 and insanely important for your differential equations. This section. So, no jokes here, right? Extremely important. So now, I have 0 over 0. We call this the indeterminate form. And we are now able, because this condition is satisfied, we are able to use L'Hopital's rule. Now, this is the way you denote that you are using L'Hopital's rule. You put L'(h) on the equal sign, because the two functions will not be equal. They just have equal answers, equal results, but the functions are not the same at all. You will be taking separate derivatives of numerator. Derivative of sine is cosine x, and derivative in the denominator is 1. And now this becomes a very simple limit, 1 over 1 equals 1, and that's how you end up with having the limit from chapter 3 that you were told, this is what it is, don't worry about it, right? Now you actually have the way to compute this one. So, with this being said, we can write the L'Hopital's rule theorem, which is again Bernoulli's rule. So theorem goes like this. If we have indeterminate form of 0 over 0 or infinity over infinity, then limit x goes to a of f of x divided by g of x is equal, and then you put the L'Hopital up there, to the limit x goes to a of f prime of x divided by g prime of x. So that's the thing. That's what we are working on. And you already saw the first example. Now we can use this on good old examples from chapter 2 for polynomials. If you remember, let's say, let's go with x squared 8x minus 1 divided by 3x squared plus 6. Do we remember what this limit was in good old times? You know that the final is in 3 weeks, right? No, we're not going to do that. It was just...
oh, it's just the...
So what's the answer?
No, it's 1 over 3.
1 over 3. You know the exponents are the same, so it's just front coefficients, right? So you already know that because you in pre-calc you learned horizontal asymptote like this way. In Calc 1 we learned that the limit you can divide everywhere by x squared. All of the other ones will go to 0 and you just have 1 over 3. So you know already 2 different ways to deal with this particular limit. And now we learn the best way. So what happens when I plug in infinity? Infinity squared is infinity plus another infinity and then minus 1 divided by infinity. So this is indeterminate form, infinity over infinity, which means that I can use the L'Hopital's rule to take the derivatives and then see what else I can do. So now, when you look at this, it's still indeterminate form infinity over infinity, because when you plug in infinity for these x's, you still have the same indeterminate form. So now, you can do L'Hopital rule again. And you can do this as many times as necessary. In this case, it's only twice. So now you get 2 divided by 6, and that's just 1/3. Trying to log in over here. Please don't ask me to solve puzzles and things. Ah, crosswalks here, here, here. More crosswalks here, here, here. Anywhere else? No more crosswalks. Verify. Thank you. Do you want cookies? Yes. Every time, without a fail. I hate this company. Offering me cookies for a year now. And guess what? Never. Never delivered. Again, cookies? Yes. Perfect. So now we're just going to do a few examples, and then we're going to work on those extra examples. So, limit x goes to 0 of square root of 9 plus 3x minus 3 divided by x. So, is this indeterminate form? Yes, it is, right? You plug in 0 for x, you get square root of 9, which is 3, 3 minus 3 is 0, divided by 0. So, when you compute this by plugging 0 in, you get 0 over 0 indeterminate form, which means that we can unleash L'Hopital upon this problem. So what do we do? Well, the easy denominator, right? Derivative of x is 1. Again, not a quotient rule. These are 2 independent derivatives. We see that, right? Derivative of f, derivative of g, not... I should write this I already used red. Not a quotient rule. Not the quotient rule. These are independent derivatives. Can be a little bit. Come on, go away. Dramatic over here. There we go. So now, the derivative, I have to take derivative of the square root. Derivative of minus 3 is just 0, so that's gone. We know it's divided by 2 times the same square root, and then plus the derivative of the argument on top. So there it is. And now you try to plug in the limit. Oh, try to plug in 0 now and see what happens. So this becomes the limit. X goes to 0 of 3 over 2 square root of 9 plus 3x. So when you plug in 0, the 3x dies. And then you have 3 divided by 2 times square root of 9. This cancels and you get 1/2. Which is our problem. So we have 1/2 on that one. Yes.
What if just the denominator is 0, but the numerator?
Can't use L'Hopital rule.
Oh.
See over here? If we have one of these two.
Okay.
So if you don't have them, you don't get to use it.
Okay.
All right, try this one on your own. This one sounds familiar. I think I had this one on my exam last semester or last year or something. This exact question. So what we plug in 0, e to the 0 is 1. So 1 minus 0 minus 1 is 0. And then 0 squared is 0. So we have indeterminate form immediately. Put the L'Hopital there. Limit x goes to 0. Derivatives. E to the x is e to the x minus 1 divided by 2x. Plug in 0 again. We get again 0 over 0. Very good. So we have 0 over 0 again because e to the 0 is 1. 1 minus 1 is 0 divided by 0. So we can use L'Hopital again to get limit e to the x divided by 2. And then we get half as the answer, right? Because when you plug in 0, e to the 0 is going to be 1. And there we have it. Yay. That's that part. So these are the two vanilla cases. This is your base, and all other cases will refer back to these. So now we're going to talk about infinity minus infinity, infinity times 0, 0 to 0, 1 to infinity, all of these other combinations. And all we're going to learn are the tricks, algebraic manipulations, to massage those problems into these. And then we use L'Hopital rule. So L'Hopital rule only applies for 0 over 0 and infinity over infinity. So those are the only two cases that you get to solve with L'Hopital rule. Everything else has to convert into this, and then we get to use L'Hopital. So the first set of these should be 0 times infinity, and then that will lead into infinity minus infinity and so on. So now here, 0 times infinity case. So that's a subtitle now. 0 times infinity case. So let's take a look at the problem. Let's actually find the first problem they do in the book is just absolutely diabolical. So let's find something that it's user friendly. They don't have them separated by sections. They're just dumped 83 problems on a pile in a textbook, and then you sort them out. So good luck. All right, so make sure you have these subtitles so that you can quickly come up. Now I gotta stare at this. There's one. This is problem 54 in a textbook. Limit x approaches 1 from the left. So you put this little minus on top of 1 minus x times the tangent of pi x over 2. Okay, so what you have in this case is, as you can see, there I say clearly, 0 times infinity case. Because tangent of pi over 2 is infinity, and 1 minus 1 is 0, so you have 0 times infinity case. So how do we deal with this? Well, we have to transform this into one of our other cases. Now, what is the trick that we are using? We're using the trick that f of x is equal to 1 divided by 1 over f of x. So it's a very cheap algebra trick. So this is what we use. And this is the only trick you have. There's nothing else. So you remember this one, so use this all the time. So what do? You take, if you call this f and you call this g, it doesn't matter, right? So you will transform. Now we're doing mathematical manipulation here, so we are not changing the problem. We're just changing the appearance of the problem, right? Same U, different shirt. That's technically what it is. So 1 divided by 1 minus x. So 1 minus x is f, and then you put that in the denominator as 1 over f. If you are to work out double fraction here, this 1 over x would go all the way up and multiply the tangent. So all I have done is this mathematical manipulation. This is algebra, and the only trick you need to know. Now if you check your L'Hopital rule, you have infinity divided by infinity, which is the indeterminate form, and we can just use our derivatives. So this one trick, a single trick, transforms 0 times infinity into either 0 over 0 or infinity over infinity. So now, unleash L'Hopital. What is the derivative of tangent? Secant squared of pi x over 2, and then we need pi over 2 in front, right? As a chain rule. And what's the derivative of 1 over 1 minus x? So this is raised to, you can do the derivative on the side, which is the derivative of, I'll show you the easier way to do this, but, so it's like this, right? So it's going to be negative 1 minus x. So this negative 1 is the exponent dropping down, and then becomes minus 2, and then the derivative of the inside. So it's 1 over 1 minus x squared. That's what it is. Now let me show you the easier way to do this derivative. If you are taking the derivative of 1 over 1 minus x, you select this, and then you push the math button, and then you go, no. And then you click over here on the pull down menu, you say differentiate. And it gives you 1 over. So that's the faster way to differentiate. Like so. Just need to make sure that you. Alright. So now, should I install this button on your exam? It's good. Right. And on your pencils, the button that you use to select is right here on the side. It's a quick. All right, so what do we have now? When I plug in, what's the secant of this, right? The secant is 1 over cosine, right? And let's see. We have the limit, x goes to 1 minus. Try to fix this. This 1 minus x squared will go there. Then I still have this pi over 2. Secant squared pi over x squared. And when you plug in, this is going to be a 0 over here. And then secant, because it's a cosine, still infinity, so we haven't achieved anything. Right? So when you run into this situation where you differentiated and you got nowhere, you turn this around. Use the other function to flip and keep the previous function in spot. Yes?
You say you got nowhere. How do you know you're nowhere?
I got nowhere because if I plug in now 1, this part is 0 and this part is infinity. So I went from 0 times infinity into infinity over infinity to go back to 0 times infinity, so I got nowhere. So when this happens, and I'm really happy that it happened on our first case over here, we are going to now abandon, and we're going to go back, and now we're going to pick differently. So I'm going to keep 1 minus x here, and 1 over tangent pi x over 2 goes in denominator. So I used the same trick, I just used it on a different function. That's all I did. I haven't switched the method or anything like that. Instead of pushing this to go into denominator, I switched, and now I pushed this, and I'm still using the same way to achieve that. Now I know that 1 over tangent is cotangent, so I have limit x goes to 1 minus, of 1 minus x divided by the cotangent pi x over 2. So now when I check, I have, so I transform this, right? When I plug in 1, I get a 0 here, and now I have a cotangent of pi x over 2. Cotangent of pi over 2 is 0. So cotangent graph, for those of you that do not remember, looks like this between 0 and pi. So it crosses the x-axis at pi over 2. So pi over 2 gives you, cotangent of pi over 2 gives you 0 as the answer. All right, so now we have 0 over 0 situation, and this is the time when we unleash L'Hopital to take independent derivatives. So limit x goes to 1 minus. We have negative 1 in the numerator, and derivative of cotangent is very good. I gave you enough time. Negative pi over 2 cosecant squared pi x over 2. All right. So now, how much is the cosecant? Cosecant, guys, cosecant is 1 over sine, right? And sine of pi over 2 is 1. So you have 1 squared. So you have negative 1 divided by negative pi over 2, which is 2 over pi as the limit. If you flipping one function in the denominator doesn't work, then you immediately go and you flip the other function into denominator, and you go from there. Let's take a look at another example for this. So we are looking for multiplication of these two. I want to see if there is anything that is user friendly, but no. There's just no. They have a lot of trig one. Well, actually, let's go now. And I don't generally like to work the ones that are worked in a textbook because you know all the letters. You can read that on your own. Right? Right. But I just don't have enough problems given. So we'll make an exception here. Limit of x squared times sine of 1 over 4x squared as x goes to infinity. So this is another one of those 0 times infinity, right? Because when you plug in infinity, you get infinity for x squared. And 1 over infinity is 0, sine of 0 is 0, so you have infinity times 0. And you can flip either 1 to start off. If it gets bad, you just go back and you switch it. So let's go and flip the x squared. So we get 1 over x squared. And we have our sine 1 over 4x squared. Stay as is. So now when you plug in, you get 0 over 0. And this is situation for L'Hopital. So what do I have? Limit x goes to infinity. The derivative in the numerator. The derivative of sine is cosine of 1 over 4x squared. And now I have to multiply this by the derivative here, which is 1/4. And then you have negative 3 x to the negative 3. No, negative 2 x to the negative 3. And in the denominator you have negative 2 times x to the negative 3. Yes. Great. So now these cancel, as you can see, and we are left with the limit x goes to infinity of just 1/4 cosine 1 over 4x squared. When I plug in infinity, I get 1/4 cosine of 0, which is 1/4 times 1, which is 1/4. So $1 million question. How much is 0 times infinity? Clearly 1/4, right? How cool is that? Is it always 1/4? No, because previous problem was 2 over pi, right? So 0 times infinity depends, right, which way you want to look at it. But right, we get these things. It's amazing. So next time, right. Also, can we divide by 0? Apparently. Only if you check. Nice. Cool, right? So we got 0 over 0, infinity over infinity, and now 0 times infinity using. All right, so we have 0 divided by 0 and infinity over infinity. That's our base. If you have 0 times infinity, use f of x equals 1 over f of x. Great. We are moving along. What's next? Infinity minus infinity case. How much is infinity minus infinity?
0.
Right? Let's get 3/4 or something. Just because you said so, right? Infinity minus infinity. How do you know if you have infinity minus infinity? Well, you plug the values in, and that's what it worked out to be. So let's see if we can find a problem that it's infinity minus infinity. Do you have anything in here? Oh, beautiful. All right. You're going to love to hate these kids. Problem 64 says, limit x goes to infinity of x minus the square root of x squared plus 4x. So first, convince yourself that this is infinity minus infinity case. So we have infinity minus infinity. What do I do? Well, I said at the beginning of the class, lecture, right? The only two cases that you can solve are 0 over 0 and infinity over infinity. That's it, right? And they're both division. The one before that was multiplication, and we switched it into division using the trick, right? Now you have subtraction. If you just think, right? what kind of manipulation you have to do to go all the way from subtraction into division? Yes?
Factors.
Beautiful. Factoring. Now, where is that going to land you? Factoring is going to land you into what operation? When you factor, what do you get? You always get multiplication, right? So, you see where these problems are going to go, right? You will have to factor to get here. And then you use this trick to go up there. I know, right? I mean, if this is not clear, I completely understand. So we have to play this game, right? You have subtraction to go all the way into division because our base cases work in division. What we have to do is we do the factoring first to get rid of subtraction. Now we have multiplication. Use the trick to go back to division, and then we can unleash L'Hopital. Well, the problem is that I can't really factor here, right? Because this is one term, this is the other term. Like, what do I factor, right? So I first need an x to factor, and I see x squared. I need more stuff. So more algebra here. We're going to have x minus, and then I'm going to factor out x squared and get 1 minus 4 over x. Hello, algebra. What have I done? I technically multiplied and divided by x over here, so I can factor out x squared. Bueno? See. All right. So now, this x squared jumps out, and it becomes x minus x square root of 1 minus 4 over x. And finally, I can factor out an x. Oops. All of this is algebra. Painful, right? But necessary. So we went from infinity minus infinity to infinity times 0. We're not there yet, right? Now we get to use 1 minus square root of 1 over 4 over x divided by 1 over x. So I'll put it in blue. From here to here, use f equals 1 over f. And I am finally now at 0 over 0. I can use L'Hopital. So about 1 page of algebra to get to the point where we can use L'Hopital rule, right? So infinity minus infinity is a case that you really want to practice, and then next time the Thanksgiving, right, lead with this example. Yeah. Everyone will know what's up immediately. So now equals, right, with the L'Hopital, these all have equal sign in front. equal to the previous line. So now finally we get to do the L'Hopital. We have the limit x goes to infinity, and we take our derivatives. Derivative of 1 in the numerator, derivative of 1 is just 0. There is a minus sign that you have to copy. And now the derivative of the square root. What's the derivative of the square root? Well, the derivative of the square root is 1 over 2 times the same square root times the derivative of the inside. And the derivative of the inside is going to be negative, and then another negative becomes positive 4 over x squared. And denominator is negative 1 over x squared. If you're having any issues with this, remember you can always use the button. If the derivatives are not, right? So 1 minus the square root of 1 minus 4 divided by x. Remember, you just select this. And then you push math. Yeah. He always reads my 4s as a C1. I'm not sure why. It's a 4. Select math. Differentiate. And there you go. All right, they stuffed the x cubed there. All right, we have better form. So now, remember how you had those complex fractions to clear in intermediate algebra? And probably, you know, many of you were like, why? And we were just, it's just mathematical gymnastics, just do it, all right? It's a section. There it is. Double complex fractions, right? So a negative will kill a negative, and x squared will kill an x squared. So this whole thing becomes the limit x goes to infinity. And what's left? 4 divided by 2 cancels. Let's do that in blue. So the whole thing is 2 divided by the square root of 1 minus 4 over x, which is 2. Hey, infinity minus infinity is 2 this time around. When I change functions a little bit, it will be different. So great, right? I'm so happy. Little bit of a stretch and a problem, but doable. So infinity minus infinity case, we use factoring to turn it into multiplication. We use our division algebra trick to turn it into division. Finally, it's 0 over 0. We use L'Hopital. The derivatives kick in. You check. Maybe you have to use L'Hopital again. Right? Depends on you know, the spice level of the problem. And then, is this hard? No. Is it annoying? Yes. Right? Those are two different concepts. Right? This is highly annoying because there's a lot of calculations. Let's see what else we can. Problem 60s. This problem looks really cute. So we have x over x minus 1 minus x over ln x. Is this infinity minus infinity? Yes, it is, right? So for infinity minus infinity cases, we know the roadmap. factor, and that will land you into 0 times infinity. And then next one is use f equals 1 over f, and then 3 use L'Hopital, and finally 4 win. So try this. What do we get to factor here? X. Very good. So let's see. Okay. Okay, so once you factored your x, you have what? You have a problem. When you factor an x, is it 0 times infinity?
No, it's still subtraction.
It's still a subtraction, okay. So, what should we do?
I made it into the problem.
Yeah, as I said, it's evil. Mm-hmm.
Can you, like, if you have like a product, and one of them you can use as rule, but the other one you can't, does that count? Yeah?
This is an amazing problem. Suggestions? So, can we factor? First, is this infinity over infinity? The answer is, infinity minus infinity. Yes, because you have 1 over 0 minus 1 over 0. So that's infinity minus infinity. But then, what should we do? If I factor out x, then I don't have infinity, right?
Can you treat them as like two separate ones and use
So
the rule?
give limit to each.
Yeah.
I like that thinking. Unfortunately, it doesn't work, but I love it because it's a really good troubleshooting thing, right? Because you are going to get 1 over infinity for each. So limit of 1 over infinity, and then what?
Well, then you can multiply by infinity on both of them.
You can't do that. It's not an equation. You have to multiply and divide each term all the time. Mm-hmm. Evil, evil, evil. All right, so let's try and see if we can just do some very basic common denominator. See what happens. We are subtracting 2 fractions. We're out of options. So let's hope that works, right? Because factoring an x is not going to give us what we want. So what am I going to do? I'm going to go and say limit x goes to 1 minus, and now is just going to be x minus 1 times ln x, x ln x minus x squared plus x. And let me see what I get in this case. When I plug in 1, I get 1 times 0 minus 1 minus 1 divided by 0. I copied all of these, right? Minus there and minus there, minus there, minus there, okay. I get 0 times 0 here. So 1 minus 1 times 0 minus 1 squared. Oh no, this is a plus 1 here, sorry. Plus 1, there we go. So do we see that we have 0 over 0? So common denominator helped. So we are going to use L'Hopital rule here and take independent derivatives. So now I have a product rule over here, which is copy the first derivative of the second plus copy the second derivative of the first, minus 2x plus 1, divided by the derivative here is just going to be 1, and then 1 over x. So these will cancel. 1 plus 1 is 2. So limit x goes to 1 minus. In the denominator I have 1 over x. In the numerator I have ln x minus 2x plus 2, because this gives me 1, and then 1 plus 1 is 2. Now, it's a double fraction, so I can kick this x in the numerator. And this just becomes x ln x minus 2x squared plus 2x. When I plug in 1, I get 1 times 0 minus 2 plus 2, and the whole thing is 0. How would you verify this? Plug it into Wolfram Alpha, right? S is for limit. I wanted to see if Simulab can do it, and they can't. So Simulab did not code this yet. But we don't need any of that stuff. What is the essence of the limit? What is it computing? It's computing the y value at the point it approaches, right? So we better see graph crossing or being close to y equals 0 at x equals 1. So you just need to graph this in any graphing utility you have. We use Desmos, right? In this day and age. So all I'm going to do is I'm going to graph this function. So I'm graphing x divided by x minus 1. That's wrong. So x divided by x minus 1 minus x divided by ln x. What? The answer as approaching 1 should be negative 1. So where's the mistake now? Cross multiply. X minus 1, I said that's ln x, that's x plus x. It's 0 over 0 because when this is 1, that's 0. So that's a 1. Minus 1 plus 1, that cancels, so 0 over 0. Derivative. Copy the first, derivative of the second, plus copy the second, derivative of first is 1. These guys cancel. So you just have 1 there. Derivative of x squared is 2x, derivative of x is 1. 1 plus 1 is 2, minus 2x, ln x, 1 over x. Plug in the limit, the first one dies because 1 times 0. Minus 2 plus 2 equal to 0. So I'm going to now verify this in Wolfram alpha, but it makes no sense because calculation is solid and the graph doesn't agree. And I graphed it right. X over x minus 1 minus x over ln x. Limit of x over x minus 1 minus x over ln x as x goes to 1. Well, Wolfram is giving negative 1/2, which is what Desmos gives. Negative 1/2. I don't see where the negative 1 where is that coming from? Can anyone find the mistake? Because I can't. I can't find the mistake. Copy the first, derivative of the second, plus copy the second, derivative of the first, minus copy. I really don't know. I'll have to do this on Mathematica to I'll have to look at this. I don't want to waste time now. So, no, negative 1/2. We see it from the graph, and Wolfram says the same. I just don't know what the steps are. I can't find the mistake. It's somewhere over here, but I really can't spend the whole class fixing this. So we'll have to go back.
Isn't there this one from like where we use the rule when we did x naturally over x and the derivative of it, isn't it going to be 1 by x instead of x 1 by x? First we're going to use multiplication. Correctly?
Yeah, I did that. I did that. Because when derivative of this is here.
Isn't it going to be just 1 by x plus naturally over x?
No, you have to copy the first, and then the derivative of the second, which is ln x, is 1 over x. They cancel and it becomes 1. And then that one plus this one is 2.
Oh,
Yeah, meditate on this, I will. I'll have to see what the issue is. But that's the case of infinity minus infinity. We can try. Want to try another one? Infinity minus infinity. Tangent minus secant. Limit as theta goes to pi over 2 from the left. Tangent theta minus secant theta. So what is the trick? Excellent. So tangent is sine theta over cosine theta minus 1 over cosine theta, and we factor out 1 over cosine theta. Which leaves us with sine theta minus 1. So now cosine theta pi over 2, that's going to be infinity, 1 over infinity, so that part is 0. And sine of pi over 2 is 1, cosine of pi over 2 is 0, so 1 over 0 is infinity. Sine of pi over 2 is 1, 1 minus 1 is 0, so I have infinity times 0. And now we switch the stuff around. So this is, let's leave sine theta minus 1 here, divided by 1 over 1 cosine theta should just be cosine theta, right? And now when I plug in, I get 0 over 0, right? So this is 0 over 0. And this is where L'Hopital kicks in. Derivative of sine is cosine theta divided by negative sine theta, which is 0 over negative 1, equal to 0. So there's that.
Question.
Yes,
Do you have to do, because I have the same answer, but I skipped a step.
that's fine.
That's fine.
Such is life. You were able to do it, right? The last case. Should we take a break or do the last case? Last case. Last case and then leave 5 minutes early rather than break and then do the last case. All right. The last case is the group of all exponential cases, and we just put them on the pile. So 1 to infinity, 0 to 0, and infinity to 0 cases. Isn't it 1 to infinity just 1, because 1 times 1 is 1, times 1 is 1, times 1 is 1, times 1 is 1, right? Maybe exactly. Wow, that's an amazing one, right? Now 0 raised to 0. Yeah, because anything raised to the 0 is 1, but then 0 times 0 times 0 times 0 times 0 somehow needs to be 1. You see where they, right? It's like a tug and pull, right? Like it starts. Oh, are you plugging that in the calculator?
Yeah.
Oh.
Just says error.
Oh, okay. Good. To make sure, I never know what would happen. So yeah, a little bit dramatic, but all of these problems will be solved by ln both sides and then kill that exponent because it drops in front. So all of these cases will be solved using the logarithmic approach. So here, use ln. All right. So let's take a look at the limit as n goes to infinity of 1 plus 1 over n to the n. Would you agree that this is a case of 1 to infinity? You would, right?
Yeah.
Because when n is infinity, 1 over infinity is 0. So 1 plus 0 is 1 to infinity. So 1 to infinity. And naturally, right, we just want to write 1 and walk away because 1 times 1 times 1 times 1. But no, it's not going to work out that way. Such is life, right? So let's go and work out the magic. So y is equal to the limit n goes to infinity of 1 plus 1 over n to the n. I have to start with this y equals because now I need two sides because I need to ln both sides. So I put ln on both sides. If you take advanced calculus, 300 or 400 level when you ship out of here, you will actually have proofs to show that ln needs to be increasing function and some other specs on it in order for this switch to occur. Right now we don't worry about that. You will worry about those details if you become math major. So we can switch the order of limit and ln. And there are conditions for that. It's not automatic, right? It doesn't work for all functions, but it does work for those increasing and positive and stuff like that. So now, what I do is I take this n, and that n drops in front of ln. So now I have ln y is equal to the limit n goes to infinity of n ln 1 plus 1 over n. And do we all see infinity times 0 finally? I hope you do. Infinity times 0, because 1 over n is 1 over infinity, 0. ln of 1 is 0, because that goes away. ln of 1 is 0, so I have infinity times 0, and now I can use the good old f is equal 1 over f. So ln y is limit n goes to infinity ln 1 plus 1 over n divided by 1 over n. Yay! 0 over 0. Unleash l'hôpital. So we have limit n goes to infinity, and then its derivative on top, which is negative 1 over n squared. And you have negative 1 over n squared in denominator as well. So now these cancel, and you are left with ln y is equal to the limit n goes to infinity. You are left with 1 over 1 plus 1 over n. Well, that's all equal to 1, because 1 over n is 0, so 1 divided by 1 is 1. And look what we got. ln y is equal to 1. E both sides to get y alone. You get that y is equal to e to the 1, which is e. Let me just write e. Now, what was y? Y was limit n goes to infinity of 1 plus 1 over n to the n. So if y is equal to y, then the limit n goes to infinity of 1 plus 1 over n to the n is equal to e. Hello, definition for e. This is not going to go away anytime soon. You will see this over and over and over again. And how about you save yourself a page of calculation and remember the formula for e? Because it is going to show up again in differential equations, in Calculus 2. Definition for e. It's going to be there. So I am actually going to box this result, even though this was just an exercise for us to calculate the L'Hopital rule. And I'll write definition for number E. Now I am going to give you other flavors. You know, when you go to the ice cream place, it's not just vanilla. You have other things. So limit n goes to infinity of 1 plus a over n to the n is going to be e to the a. And then limit n goes to infinity of 1 plus a over n bn is equal to e to the ab. So these are all shortcuts, because the problems that you guys are going to see in the future, especially Calc 2, are going to look like limit n goes to infinity of 1 plus 3 over n to the n. It's just better if you know immediately that it's e cubed, rather than cranking the full page of calculations. So you are doing yourself a favor. If you're going to Calc 2, you're doing yourself a favor of working this out. Okay, what other cool, cute problems can we score in here? Oh, beautiful. Limit theta goes to 0 plus of sine theta raised to tangent theta. This is poetry. There's no numbers here, just letters. This is all, by the way. It's all positive, it's blood. This is what mathematical poetry looks like. No numbers. All the steps are the same. Y equals, and then ln both sides, tangent jumps in front, and then you go, you know, one by one. So as you can see, more of the same. ln both sides, tangent jumps in front of ln. Then you have 0 times infinity. Put the tangent as 1 over tangent, which is cotangent, in denominator. You have infinity over infinity. Take independent derivatives. And when you take independent derivatives, work out a double. This is 1 over sine squared. So one of the sine cancels and the other sine multiplies the cosine. Minus times minus positive. So sine times cosine, which is 0 times 1, which is 0. E to the 0 is 1. And since you define your y to be the entire function with the limit, so if y is 1 and y is limit, then the limit is 1. Is this used at all? Of course it's used. All the time. Right? These are the limits that you are actually going to see most of the time in your 300 and 400 courses. The first word problem that they have, optics, physics, right? Plus, you know, some people would go into that field, right? So what do we have? The theory of interference of coherent oscillators require the limit, right? And then they show you, so sine squared divided by sine squared. So you have 0 over 0, you keep taking derivatives, and then those extra n's pop out to get n squared. So it's used, it's all over the place. You just need to practice. They give you 83 exercises that are like this, plus additional 20 word problems to try. This is one of the lectures, one of the lessons and sections that I star and flag for Calculus 2. There will be certain lessons that you absolutely must know, plus some of the trig formulas if you are planning on going into Calc 2, and this is on the list of those. So far, you guys covered for Calc 2, you covered your limits in 2.3, you covered your chain rule in, I think, was 3.7. You covered L'Hopital's rule. You are going to do basic integrals in 4.9 and use substitution in 5.5. So these are the sections from Calculus 1. And before this, you will have trig identities. I will give the overview of things that you must practice and know before you venture into Calc 2. Otherwise, it's slaughter, immediate slaughter. That's what it is. Calc 2 has reputation. Some of you already know it. The other ones just learned of it, right? So if you know these sections back and forth, Calc 2 is going to be a joke. If you don't know it, then you get to discover 7 or 9 levels of hell, one by one. Going, I'm not sure. I have to go back to Dante's Inferno and read it again. But yeah.
6. I think I'm right. 7.
Yeah, I think 7 too.
Well,
So, but you will spawn all 7 of those, right? As you go into Calc 2 without this list here. So next class on Wednesday, we are going to take a look at 4.9, which is labeled anti-derivatives which is integration. And then chapter 5, 5 sections, 2 of which are extremely short. 5 sections of integration, culminating with 5.5, which is use substitution, which is the chain rule backwards. You will learn next class that antiderivatives, also known as integrals, are backwards derivatives. So you will be able to take a function and find another function that if you take the derivative of, you will go back. And we'll do that next class. And after integration, the course is over. So we have 3 weeks left, and I will be scheduling a review session on the reading day. That's the day when you don't have any classes. Reading day is the day before final exams, and that review session will review all of your Calculus1 in preparation for. It will be in the evening hours, again during our regular class time to accommodate all of you who work those long hours. And it will also be open to the Saturday Calculus1 students, so we might have additional, 5 or 6 people come in if you all show up. It is optional, obviously, and it will be there for the review. Now we still have an exam, 3, if you want one, and since on Wednesday, we can either vote today or we can vote on Wednesday about the date for that exam. Wednesday? So Wednesday, 4.9 and 5.1 at the minimum. Maybe we peak into 5.2, I don't know. We do have over 3 hours, I think 3 hours and 15 minutes our class, right? So we might even peak into 5.2, but we will definitely then make a decision. So be here, right, on, we are starting integration next class. You do not want to miss that, right? Your calculus is limits, derivatives, and then integrals. So you do not want to miss that third part of calculus. Yes?